So what did people think of the simulation, the simulator? Thumbs up.
There were some intricacies that presented difficulties I didn't foresee.
So the intricacies that you did not anticipate. More on the radar side or the coding side?
Well, first, it was a little bit slightly more meticulous to sort all the actual times into forcibly resolved range gates.
Yes.
And then plotting that was sort of a pain in the butt for some really stupid reasons.
Yeah.
That
Yeah. So it's there's the radar, there's the physics, there's the concepts, but then actually getting the MATLAB code or whatever code you're using to get what you want it to do. Yeah. That was the hardest step? Yeah. Yeah. And that's why I wanted to do the simulation early, in the concept of how to visualize data. And here you're creating data and making a visualization of it. Yes?
So one thing that I noticed that at first I thought maybe I'm wrong is that it's supposed to be at 10 kilometers, right? But then since you have the range gate, it shows up at the 10 kilometer and 200 meters. I think that those were, and then I realized that was right. I did the math. I was just wondering though. I used a logic that just selected the range. I don't know if my logic is the best, but anyway, I have a logic that just checks the range gates and the times of arrival and just says, oh, this range gate was triggered and not the other ones. I was wondering, in real radars, do more than one range gate get triggered for the same signal? And if so, are we going to simulate that, or should we simulate that?
So that's the difference between, right now I just started to go into my answers to the last sentence that you said I didn't hear. But the concept of, when I was a little hesitant last week or the week before, should we do the radar simulator? It's a target radar simulator where we're taking the target, calculating its exact value, and then projecting it into what a radar would see.
No distribution of
Yes.
gates. Okay.
But what a real radar does is it transmits a pulse, and then for every A to D, it makes a sample.
Mm-hmm.
And part of what we talked in the lectures was that it's going to measure a noise number. There will be a noise number, and then added to that will be a target power. And some gates will have power from a target, others will not. And so it goes and it collects, in our case, 240 range gate samples. It would go and grab 240 samples and put it to memory. It might be a short-term memory, but it will grab it and put it to memory. That's quick time. All that information is about range. Then you go slow time to the next transmitted pulse. Transmit a pulse, collect 240 samples. If there's information in a range gate, it is detected and saved. And then that's repeated. So that sequence there is also called a dwell engine. If you were to create code, you would create a dwell engine that would say, what's your trigger? Start your trigger. Tell the transmitter to start making a pulse. It will create a pulse. Then there'll be, part of your logic would be, tell the receiver, do not collect any information, blank it, until you know it's safe for there to be not any power coming back. Your next part of your dwell engine would say, collect a sample, and then delay, sample, delay, sample. That would be one IPP. And there's the logic that you would create. And then you'd go and repeat that exact same thing for however often you do that mode. So that's a dwell engine. So this is part of the radar systems aspect.
And then do you iterate through the gates? Is that something you would do in a simulation, just iterate through each gate and just figure out, was there power there from the target, was there power there from noise, or just draw us a distribution for noise? Maybe if it's random Gaussian noise, you just...
So what was the first word you...
do you iterate, like to have a for loop? Yeah, iterate. You just have a for loop that is going to go for each range gate and just figure out, for range gate number 1, we have the target. For 2, we don't have the target, but we have noise. Is that how you would figure out which value goes in each ADD channel or something?
The way I would like you to think about it is that for the simulator, we are moving the target in to create, right now it's just power, and some people added noise to that, and the noise is not fluctuating. But you have a sample, and you will collect 240 range gates, and then after you're all done, then you put that aside, and then that's when I want you to come back and say, given this signal to noise in this range gate, is there anything for me to process? And so it's done after the fact. Because what's going to happen is that the radar is going to be in space, it's going to make its data collection, and it's going to download its data, and then you, as a scientist, would then process that data and determine where you have targets, where you don't have targets. That's good questions. So what we're going to do today is expect about an hour and a half, because we've had an hour of lecture. I'll be here until there are no more questions. We can turn off the recording if we want to, if there aren't any questions, and just one-on-one conversations. I've changed our homework for the next week. That what I'd like to do is that there's a lot of reading for the next 2 weeks. So next week there isn't going to be no homework due next week. I will create the questions this weekend, and then they'll be due in 2 weeks. So, and those questions would be what's pertinent for the exam. So we'll go over the changes in detail, and then I want to review the exam, because that's in 3 weeks, right? The 20th. The dates will be there. Yeah, because we have 2 more lectures than the exam. Then go through the radar simulator, and then highlight the 3 different elements of losses, noise, and signal. And then open for questions. Any changes to this agenda? Additions? Okay. So what I'd like to do, so I've updated the schedule, I've put it onto D2L, and so basically there's no homework due next week because there's a lot of reading that I was originally scheduled for week 5, but we'll do some reading next week. I'll move this homework due in 2 weeks, and then the simulator number 2, move it after the exam. Because it's good, and we'll talk about what value the simulator provides to understand our concepts. But I think there's some bigger ideas that I'd like you to grasp before the exam. So on the D2L, these are the 2 documents that you'll find that have the schedule. So what's in red are the changes, and then this is the cleaned up version if you were just to look at it clean. We are at this point here. You submitted the simulation, and I'll create a video on electromagnetic review. I want to make sure that my syntax is the same as the syntax that's used in the book. And then we'll cover radar antenna basics. We'll get into more detail of antennas and dealing with phasing after the exam. Then we'll have a homework due in 2 weeks, and then the in-class exam. Does this make sense? That I don't want to be teaching to the exam, but right now, you guys can construct an ideal radar. You know how our radar works, the pulsing, the power coming back. This is the ideal radar. Now, basically for the rest of the class, of course, we're going to talk about the problems of radar. and also pull out some information to get more information out. But right now, you could describe how radars work at a cocktail party, at that level of how does it work. But I really want also to talk about volume scattering and surface scattering for the exam, because that's how we would be using the radars for environmental purposes. Okay, then the second page is that I've moved the simulation for number 2 past the exam, because we can actually get into some phasing information, and yeah. So exam details. So we're still on schedule. This is unchanged. Have our in-class exam the 23rd, go from 5 to 7. Closed book, closed notes, open simple calculator. And for distance students, I need to connect with you to make sure it's a proctor, and also that I'm available for if you have any questions during that time period. If you need a different time because of your travel, work, let me know and we can arrange a different time. And then because of the distance learning and other schedules, we won't discuss the solutions until the class on the 2nd. So that's the plan. I expect to cover these materials from week 1 to 5. We're up to this point right here. And from what I've seen so far, you guys are understanding it to a level of where from a systems engineering, these are the components that you need to know. We've talked about hard target scattering. That's what your simulator was. We'll talk about volume scattering, how much now you have targets that are distributed within the volume, not just a single target. And surface scattering is when the radar is coming down and it's hitting a rough surface. Of course, show all your work, because it's the thought process that's important. And when you do the reading the next week and next 2 weeks, I kind of made the comment that I would not put this order of the material the way this author has put the material, but I haven't written a radar book. He's written at least 3 that I know of. But we're not going to do anything with phase. And by phase, I mean sine wave, cosine waves, how far is a target relative to a wavelength. That's into the details that I expect you to know later in the course. But right now, there are fundamental properties that I think that, and this is why it's an in-class exam, is that these are the principles that I would like you to know 5 years from now when you're working in industry, continuing work in industry, when someone says, this is my antenna, and you can have an intelligent conversation even though you may not be working directly with radars. Questions on expectations of the exam? And hopefully I'm setting everyone up to learn, because this is the stuff that I would want someone to know if I were to be working with them in working with radar data. Questions before we go to the simulator?
So for the exam, you probably know how to derive the power, the noise equations, and all that. Memorize is going to be terrible. You just memorize how to derive it and do that by then.
So for the range equation, there's the transmitter, there's different components. And we went through how there's different gains and losses of the components. What would be the power that's scattered from a target or received? The big picture concepts. And probably it'll be set up so that dB would work, so that it's in that space. Because that's one of the things that if you're a radar engineer, you will be thinking in signal to noise, you'll be thinking in dB as you have conversations with people. Because when someone says, I have a 3 dB change, what does that mean? A doubling of power. You don't know if it's in the transmitter, if it's in the antenna, the target. And in some cases, it doesn't matter. The antenna's fixed. The power's fixed. Now, the target has changed. It changed by 3 dB. Well, the target had to change. Or someone says, I want to spend more money and buy a bigger transmitter. Now you do a cost trade-off of more power. Is it worth the dollars? How much gain are you going to get? It might be more cost beneficial to increase the gain of the antenna. So for the radar simulator, this is my flow diagram. Define the attributes, the target attributes, initial conditions. This display, the radar target and attributes, is really to verify system performance. And before you start your simulation, where is the target? Make sure you know where it is. And remember, I had end gates set to 250, and then when I plotted it out, did the calculations, like, no, this has to be 240. Transmit pulses, so your flow diagram. I think, don't want to dwell on this. So now with the radar simulator, what questions do you have? Do you want me to show you my plots? Okay. So the first three range gates in time, these are the samples of the A to D. The last sample, 96 microseconds, is less than this IPP, the time of the next pulse. The range to the center of the first range gate was set to 120 meters. This is a test of the 60-meter delta between range gates. And the last range gate is before the maximum range of 15 kilometers. Initial target, 2 square meter cross section. It's currently at 10 kilometers away in the y-axis, but at straight bore sight. And the target is moving 60 meters per second. So these are the estimated values of the target. Range is about minus 180. These digits were because I used MATLAB and just spit it out. And noise power. So expect in the simulation to have a signal-to-noise ratio of about 27 dB. And the time to the target was 66 microseconds. And the IPP, I'm just going through this, was 100 microseconds. So that's okay. Final values, the signal-to-noise changed by a fraction of a dB, and the time to target changed by 1 microsecond. So during the 4 seconds, there were 40,000 pulses transmitted. This time of arrival, this is the time the pulse went out and back. And since the target is approaching, that time is decreasing. And this is the received power during the 4 seconds. So I want to just talk about the fast time. So this is transmitting the pulse. Transmit 1 pulse. And then each one of these gates corresponds to a range gate, but our TR was at a resolution of every 100 microseconds, and these gates have a resolution of delta T is equal to tau. Oops, I don't have to do that. 400 nanoseconds. So part of the process was how to get that exact time, how to get it into that range gate. And then once you have data in a range gate, later we're going to do time processing in the slow time domain. So this is what I came up with. You have 4 seconds, the horizontal, and range to target. The target was originally at 10 kilometers, which ended up being in this range gate. The center range gate was 20 meters taller than 10 kilometers, and that's the center of the range gate. I plotted the blue line as the position of the target. As it's progressing in time, it's approaching, and then you can see the blockiness of the resolution of the radar. So even though in our simulation the target, we know the exact time of arrival, and we can convert that time into range using the range equation of t times c divided by 2, that's the time conversion to the range. The radar has this bulky time resolution. And that time resolution, little not off topic, but this is the 400 nanoseconds. I haven't calculated this, but then the bandwidth is 1 over tau, which is 1 over 400 nanoseconds. So what's the beamwidth of the, or bandwidth of this? I don't know what it offhand, so can someone calculate that? Is that 2.5 megahertz? 2.5 megahertz. So is that right? Okay. So if you want a narrower resolution, you want narrower resolution, shorter tau, then your bandwidth's going to increase. And that's going to cost you in, you're only going to be limited in how much frequency bandwidth you can transmit, what you're allocated. So there's going to be a limit of making your pulse narrower and narrower at the expense of increasing your bandwidth of your system. And then you can plot this in some power received plus the noise power at each point. So since the noise figure was calculated or was given, you can calculate the background noise, which was it minus 106? And so every single cell, there is a noise value. And then when there's the target, it's signal plus noise. This is what was in the lecture this week. Wasn't expected for you to do that, add the noise and the power, but from now on you will. And you will be having noise that's fluctuating. So each cell will have a different noise based on the noise statistics. And then typically what you'll see in the data is that you'll work with data that's in signal to noise ratio. And what that does is it removes the absolute power. It's relative to the noise. So is your signal far away from the noise level, or are you close to noise? And now it's dependent on what's the quality of your radar, the phenomena that you're looking for, if that's proper English. But if your system has a large noise variance, all you care about is that your signal is larger than this noise variance. If you have narrower variance, it's the ratio between the signal and your noise floor that's important. So it's the ratio that will extend from one system to the other. So it's this. You can plot it in signal to noise. The next figure is just showing that this is from 0, where you have noise over noise, and it's expressed in log. Up to 30 dB. I think we had 27 dB was our threshold, or our detectable, our range. If you change the color bar to be from 27 to 28, you just see the resolution change in signal to noise. So that's what I did for the simulator. Are there questions?
I use scatter for plot. What did you use?
Yeah, that's a good question.
Scatter?
I use scatter. I don't know which one, because I couldn't figure out which one you used.
Okay.
But scatter gave me similar plot. But I was just wondering what exactly did you use? Or MATLAB?
Yes, I use pcolor.
P-color.
Pcolor is my friend.
Can you show us the command? You
Yeah.
had
Yeah.
the code up there a minute ago.
Yeah. And scatter is 3 variables. You have X,
Yeah, X, Y, and then the
color,
size point, and then the color.
and the color. Yeah.
P-color requires a matrix as one of the arguments through me, so.
Yeah, me too.
That'd be your.
The 240. Yeah, that's why I figured out eventually, but.
But then you have to send the ones with no power in them. You have to make them NANDs.
Yeah.
Oh, so that is transparent.
And then you have to turn the grid off that it uses when it.
Oh. Sounds like a pain in
So this is one of the things like, well, I could give you code, but then you're not going to learn it.
No, sure, just
Just
one.
the actual plotting is
The actual
the
plotting.
problem.
Okay, so what I also define my matrices with NANDs to begin with.
the.
Sometimes you can fit it with zeros, but I fit them with NANDs, and because I do the plot,
Zeros.
Okay. Which one is this? Yeah. So,
Look, man.
I could redact it. So this is how I get pretty colors. I like those colors.
Good.
This is time. This is the TIPP, time of each IPP. I then take off half of a step so that because P color defines this coordinate, X, Y, and it shades this color given the dimensions. So T needs to be offset by a half, delta range needs to be offset by a half. This is in meters, put it in kilometers. And then the way the matrix, sometimes you have to use the transpose. And then you have to do the shading flat and then the color bar. So shading flat removes the black lines that are the bars. Sorry, are the bars that are the grid boxes.
Thanks.
Yeah, it's kind of interesting, where are you guys in your programming skills? There's the radar stuff, but then how do you communicate and do that work? And so here are some of the skills. And now you're going to be able to do this, and you're going to be calculating complex amplitude and phase for every single target as your target is moving through the beam. So you'll get phase information as we go. That's looking forward. Questions about converting into exact time into binning? Okay. It's the current tab. I guess we can get rid of that too. While we're looking at this, I just wanted to show a figure, kind of a little bit of motivation. This is a plot that I made yesterday. So this is what I do. And on the horizontal axis is 60 minutes. And so I'm not going to write on here. So time is 60 minutes, time of hour 0. The top panel is the reflectivity. It's the power return. And height is, and it's a vertically pointing radar, and it's looking up to 4 kilometers in height. This radar is collecting data every, I think it's 30 meters. Every 30 meters. And so it's sampling, and it's whatever's in that volume, it's collecting data. And it's signal plus noise. I have thresholded the data so that the signal to noise is too low. It's just noise there, and it's looking up. It is seeing raindrops and seeing ice particles aloft. And we know that it's rain here because it's falling at 4 meters per second. And so raindrops, a 1 millimeter size raindrop, falls at 4 meters per second. And so if we're measuring a fall speed of 4 meters per second, that means there has to be raindrops present. Aloft, it's ice, and like today, it's icy, and ice doesn't fall very fast. So the top panel is power, middle is the velocity, and the bottom is spectral width, or a measure of the variance of that velocity. So while we have a single target that's coming through, and we know what the target is, and then we simulate what a radar would see, we could actually do that for every single range bin, where for a given sample of time, instead of defining one target, you would define a column. What's in the column? And you'd keep track of what's in the column from sample to sample to sample. Or a modeler has given you output from a weather forecast model, and now you have what's in the column. You can convert the ice crystals and raindrops into what a radar would see in that column and replicate what a radar would see. On TV at night, they say, here's the forecast. They show a horizontal picture of precipitation. They show also radar images, but the output from their models, they make it look like a radar. And they convert it into these powers. So this is, I'm excited about the simulator because what we're going to cover in a couple weeks is really advanced. And you can't do it. You can do it on paper, but you don't really get a feel for it unless you can crank through some numbers. Yes?
Why did you discretize it in terms of range? I guess now that I'm thinking about it, it makes more sense. But I did it in terms of time, and then I converted that time back to range. That's just to me more of how the radar would work internally, since it's measuring time.
Exactly. So the radar only measures time. So if I heard what you said is that you took the exact time from the radar, from the target.
And discretized that.
And discretized that, and you did everything in time, and you binned it in time.
Right.
And then
Convert that to a range.
And then you converted it to range.
And the range has steps.
Yes. That is proper. Because that's how a radar would think. The radar is only thinking in time domain. All it knows is it transmitted a pulse and something came back. We convert it into range. For our graphics.
So you discretize range just kind of as a shortcut, just to avoid doing the same calculation twice, basically.
You mean for this data? Or
no, for the, I'm going back to the simulator.
To the simulator.
Did you code wrong? Did you do it in terms of time?
Well, I thought I deleted my range information. I did everything in time. That it measured the time.
Oh, okay. I read your code wrong.
I do also, I had, if you see some of my code, and I have keep. That's for debugging. So if we know what the range is and you calculate the wrong range, it's a debugging variable for me. But that I think I did everything. Yeah, everything could be done in time. Where's the desktop? Okay, I guess I have to do this. keep. So can you say that again, what your question is?
For some reason, when we were going through the simulator, I thought it looked like you took the exact range, basically the true range, discretized that,
Okay.
knowing the range corresponding to each gate, each A to D gate.
Okay.
Maybe I got that wrong.
So before transmitting a pulse, the target moved a little bit. So the distance traveled in 1 IPP, target speed. And this is just a little, since I know the target's coming straight down, I didn't have to do any trig. This is the new target range. That's used in the radar equation to get PR. And from that target, this is the true time. Now that the true time is saved in for this IPP, this is the transmit time for IPP.
No, he did in time.
So this, yeah, I guess I did it twice. I did it this way is the minimization just found the closest time. It didn't do the looping.
Mm-hmm.
So I use round. Is it bad to use round?
Round what? So how to...
Round it to the nearest.
Did exactly like that.
Somebody say they did round?
Yeah, that works. That's why I did it.
So this guy, and then you get
It's equivalent, right? Is it equivalent?
minimum of the absolute value of the difference. Round. I think of round as...
I thought the keyword, the center, you said something like the center of a range gate corresponds to
Yes.
the switching or something like that. I thought
Yep.
that meant use round.
Okay. Okay. I need to think about how that would work in the MATLAB code, but yes.
Our plots look similar, so
Yeah.
I think it's equivalent.
So that it's this target, it's assigning which bin does this target fall in.
Yep.
And that's a little bit where there's not a disconnect, but we know where the target is and we're going to assign it to a radar. The radar doesn't know. It's just collecting time, and if there's something there, it returns the power. So this is the synthesis portion. Yes?
Could you explain what's in the your variable t sample times, where you find the index with that minimum of the absolute value?
Yes. So T sample times, that is the time of the A to D where it actually makes its samples. And okay. Tau is the radar pulse width, 400 nanoseconds, number of range gates, time to the first sample, time between samples. So this is the time between one ADD sample to the next. And I've made it a separate variable other than tau because you could transmit a long pulse, and we'll do pulse modulation where we'll have a long pulse, but our A to D samples will be faster than tau.
Okay, that was one thing that I missed because I didn't think of how to fit in the time to first sample and
Yeah.
stuff. So I'll talk to you after, guys, about
Okay.
my mistake.
And then I'll turn this on to the D2L that's up there.
Mine is not. It's very similar. I'm saying that your code is so much clearer than mine. It's amazing.
Oh.
Like we did something very similar, but yours is just so much prettier.
After a couple of years, your code will be right there. So, do you have questions conceptually about the radar? Well, so I have a question for you guys. We did the simulation for 4 seconds. We just transmitted 40,000 pulses. Why did we transmit so many pulses? How far did the target move from one pulse to the next?
Millimeter, I think. It's like 60 meters divided by.
So 60 meters per second, every pulse was 100 microseconds. It moved 6 millimeters. Moved 6 millimeters between a pulse. That's not very much. What was the wavelength of the radar? I don't have it here, but it'd be in the display. 3 gigahertz.
100 milliseconds.
10 centimeters. 100 millimeters. So if you have, I'm going to do this with my hands. You have a sine wave that's 100 millimeters long, and then from one pulse to the next pulse, the target moved 6 millimeters. And then it moved another 6 millimeters, and another 6 millimeters each pulse. That representation of a sine wave is what we call the phase. You're not going to be tested on this in the first part, but we transmit so many pulses because we say, relative to the wavelength of 100 millimeters, the target moved 6 millimeters. The next pulse, we could probably average together, and the target probably wouldn't move very much. But in a sine wave, if it moved 50 millimeters, we're now on the opposite side of the sine wave. We're now out of phase. So we could take several pulses, maybe 3, 4, and then we would consider that those pulses to be in phase, coherent. The target hasn't moved very much relative to the wavelength. If we change the operating frequency to a longer wavelength, lower frequency, then the target could move more before we've moved so much of a wavelength, so much of a phase. We'll get into those details, and those details are such that you wouldn't want to have to remember them, but you'd want to crunch through and be able to do the calculations of, oh, we've now moved pi over 8. I'm getting ahead, but when we run the simulator later and we calculate amplitude and phase, we're going to be keeping track of how far the target moved relative to the wavelength. Okay. Higher frequency, shorter wavelength, the shorter the decorrelation time of your target. These are the concepts that, as engineers, we would need to worry about. Yes?
But even if the correlation time is smaller, can't you put in the dynamics of that sine wave into your code so that you predict where it should be, and then you just kind of transform it so that you can integrate that with your coherent algorithm or whatever it is?
Right. So the question I heard was, can you predict? Yeah. Well, what we're going to do is we're going to do FFTs to decompose the velocity of the component. And once we know the velocity after the fact, then we'll know what's decorrelation time. But we don't know that until after we've analyzed the data. We don't know what the target's doing until after we've analyzed the data. But we set up the system to have a maximum velocity, maximum range, so that given the wavelength, what would the decorrelation time be? So yeah, that's a good question. That, yeah. That makes sense?
I knew I was wrong, but so your wavelength, it was like, and mine was 100 meters, so I was like, oh.
So what I'd like to do is go through the slides from the 2 lectures, I guess there were 3, and highlight key components of it, and then ask questions as we go, because I just don't want to have it open-ended, you know, that there are things that I think are important, that why are they important, and I want to get your feedback and understand what is difficult to comprehend, what doesn't make sense. So the first part was about noise, and that noise in a system, we always characterize it as a positive number. So this kind of makes sense that
Oh,
then
time out, time out. First part was about losses.
about losses.
Yeah, you said noise.
Oh, no, losses. Yep, losses are, it's right here, losses. Are positive values so that we can, in our log space, think of positive log in this expression are additive, and then we subtract values that are loss terms.
One question. Every text I've ever read has mismatch loss outside of the gain of the antenna. It's not included in the gain, including Bolanis does that, Krauss. I saw that in the notes and it caught me off guard.
So mismatch?
Yeah. No, it's there's an E to the R. It's a reflection coefficient. I don't know if that statement's absolutely true in all cases that mismatch is included with the lot gain of an antenna in the gain factor.
It makes sense that it would not be. That
Usually gain is directivity times efficiency.
The efficiency, and it's at the terminals. That if you have an antenna, what is the gain at the terminals? Then if you have a mismatch, that's outside of the antenna.
It's the gain of
that's a good point.
The power that gets injected into the antenna.
Mismatch that's a good point. Mismatch, receiver load. This. Let's cross that out. That's a good point. I didn't notice that it's. That is my understanding too. You have the terminals and then any mismatch is based on these terminals. Your VSWR.
Yeah, whatever gets past the mismatch is then you apply gain to.
Yeah. That's good. With different losses in the atmosphere due to rain, losses function of frequency. They're expressed in dB per kilometer. Depends on where your radar sits in the frequency. Where do you have atmospheric losses that are there due to the air of our atmosphere? Remember that for a monostatic, energy goes out and then its return path. So a loss is usually expressed as one way, but you have to account for the two-way loss, and that's done in our dB equation. Let's see. So this is from the textbook. Is this? You include all the loss between the receiver and the antenna.
So is that the L system? Those two are the system losses?
Yes.
Okay. It's written right there. Sorry.
Yeah. And then this is just an example of how to read cables and the cost differences between you could pay more, have less loss, bigger cable, how to look for these losses, what are the trade-offs. Propagation of the wave in your cable is different than in free space. You'll need to account for that in your timing. Usually there's an offset that you add to a system to account for propagation losses. Propagation percent of free propagation path, the speed of the wave, as it goes through cables. Beam shape loss. I think I mentioned that this could be considered a signal processing loss, that you don't know where your target is, and you could probably determine where your target is as you scan for it, find the target. Signal processing loss. We'll talk about calculating the FFT. This is the Doppler frequency. We have targets going away, approaching targets, and if your energy and your FFT is not exactly on the bin of your energy for your FFT, right in the center of your bin, you'll have bleeding into the neighboring bins. And we can add in our losses into our radar equation. So we have losses are usually expressed in one-way propagation losses. You need to know the length of your loss, if it's rain or fog, and then remember that's two-way for a monostatic. System losses are inside. They don't depend on the atmosphere. There's losses. Any questions on losses?
A question I have that's general is also for noise, so you can comment on that.
Yeah.
So in practice, how do you get these numbers? Because for noise, one time it looked like you just took the output and the input, maybe so a calibration would give you the number. But it also showed in this slide some of that you just find the cable and then you, in theory, find what the loss is. So in practice, what do you usually do?
So the losses are usually so system losses, where you have a cable or something that's inside your system, you would characterize it by making in the assembly process, calculate the loss, and you could add up the components, disconnect cables, send a signal through, calculate the loss, and go part by part by part and characterize the system.
Too busy calibrate it.
Calibrate it.
Measure with the VNA.
In the atmosphere, that gets a little bit more fuzzy, and it becomes now estimating what the rain is, and then by measuring the signal, if you're measuring the power at each range gate, the loss of signal as the wave propagates through the rain, because the rain is acting as it backscatters, it's also attenuating the signal that's going forward. So then it becomes a retrieval of, given this initial reflectivity or power return, as the power returns to distance, you know that it's decaying because of it's going further away from you, but is it dropping off faster because of the media? And then compared to before it rained and after it rained, the drop-off would follow the non-attenuated region. So it now becomes an iterative retrieval process of, well, what was the rain that was there that caused this attenuation? And then you iterate through. Well, was it 1 millimeter, 10 millimeter? No, 5, 6, to get that right rain rate. It's a good question. And then noise. Noise is a random process. It's going to have some value with variation. If you take your samples, 240 range gauge, if you don't have any targets out there, it's just measuring noise. So that's a good noise estimate. So oftentimes we'll transmit enough. If you're looking vertically and you're looking for rain clouds, you transmit high enough so that there aren't any clouds above you, and now you measure noise. And now you get a noise floor. Then also up here, you can send a test pulse. So now you send a little pulse, inject it into you would have a noise source here. And another circulator.
That
Or-
diagram, the dotted
Is it-
line for TE does not include the front end component, the receiver, switch, and cables. Later in the lecture, I think you do include it, which kind of confused me.
So,
The TE, receiver noise TE,
oh, okay.
the dotted box does not extend around the front end components of
No.
the antenna.
So this is the receiver components. So there would be noise that appears here.
The noise that appears there, this gets into the one thing I have trouble with. You got noise coming in from cosmic stuff that hits the antenna. I think one's TA, small a.
Yep.
One's due to the thermal temperature of the antenna. But what about noise caused by the components between the back of the antenna and the front of LNA? If they're passive, do they add noise themselves? Because they're not at absolute zero, but it conflicts with something I learned at a job interview once. Any noise that goes into a passive component generates heat, and the heat in turn generates noise, and it's an energy exchange, so they really don't add more noise. It's really confusing. It adds signal to noise because it attenuates signal, but does not add noise power because the noise power just does an energy exchange.
Okay.
Any comments on that? Because it confuses the hell out of me.
In my mind, I think about that the temperature at this point, we see that when the radome gets wet, we see the noise go up. Nothing else is happening, but you throw water on the radome of the antenna. It is now emitting at the radar frequency. So that's a noise source. These components are passive. Never think of them as adding noise to the system.
Which is a little bit confusing because they're not at absolute zero.
Not
So
absolute zero.
it seems like they should add noise, but you're correct. That's what the one gentleman told me in the interview.
So do you work with radiometers?
No.
Not at all? That radiometers they don't have an active transmitter. They just listen, and then they have a very low system noise that they then detect changes in emissions that are being detected by the antenna. That I would, again, maybe the systems that I'm used to, that there's so little loss between here
Yeah.
and here. Well, we do have cables and we calculate the loss.
So if you do it from a signal and noise ratio aspect, or a noise figure, and most of the time you put the noise figure reference to the LNA input.
Yeah.
So the noise figure, the components in front of the LNA add up, which implies that they add noise, or not so much that they add noise as that they attenuate power signal,
Right.
because signal's coherent or
Right.
not random. It's a very confusing concept that I can't get my head around. It doesn't add noise power. And I can't figure out why it doesn't, because the components are not at absolute zero.
Right. So they're affecting the.
More like there's components where at a higher temperature the noise floor would be higher,
Yeah, that's
but it's not amplifying any noise.
so. If I have two coaxial cables connected together with a 50 ohm load at the end of one, and I measure the noise power coming in, and then I take one of those cables off and I put the 50 ohm load at the shorter cable. My understanding is I would get the same noise power coming in. And what's confusing about that is, doesn't that extra length of cable add more noise just because it exists?
It is relative to the other temperatures of the system. That if you're operating at, I don't have it off the top of my head, but if you are seeing the galaxy, So here's an example. 50 megahertz radar in the tropics. It's pointing straight up. It measures the noise. It's also seeing deep space. So all deep space at 50 megahertz is coming into this antenna. The noise floor, every day, it goes up a half a dB. That peak that occurs in a 24-hour cycle, because it's going through and it sees deep space, and then it doesn't see the galaxy. And then when it sees the Milky Way, it has an increased noise. So there's an enhancement. Well, when the Earth revolves around the sun, that if this is the Milky Way, when the Earth is pointed such that the radar nadir is seeing the Milky Way, the time of day is midnight, but over here, when the radar is pointed through the sun and sees the Milky Way, it's noon. So in the course of 365 days, over the course of the year, that increase in noise floor propagates through 24 hours. Because when the Earth is here and there's increased noise from the Milky Way, this is midnight, it's 3 in the morning. This is noon, so this must be 6. So the galactic noise is increasing such that this term will have some magnitude. We don't really control it, and then you make sure your receiver is below this variation of your noise. So in your example of 2 different cables, they don't add more noise. It's because they're already pretty hot. And the change in this distance, this delta T, due to this new cable, is small relative to the temperature of the whole system.
So TE is a lot bigger, TE is a lot smaller than TA plus TA. That's, okay.
Yes.
So it does add some noise, which I was also kind of not understanding, but it's just so small compared to the rest of the receiver.
Yes. Unless you're able to get these temperatures down, then you have to spend the money to get this temperature down.
Mm-hmm.
And small enough so that if you want to see variations in the radiated temperature, then you want to have this receiver temperature small. I didn't think about this before, but that would be noon here, noon, as the Earth rotates around. Yeah, so this is that noise figure where if you have gain affects both the input signal and the input noise. If you had an ideal system, there would be no change in signal to noise, and from the input to the output, and F would be 1. But since it's active components, it's adding noise. So this kind of gets into every single, if you think of these as A to D samples, and there's going to be some mean value and some variation. This is our target coming in. At some point, we're going to have a detectable signal. We've talked about things in power, but we're going to convert this into signal to noise in a couple minutes. But noise represents some value with some spread. We treat losses as a constant unless it's atmospheric. Then there's some path length to it, and you need to estimate that loss. But we consider noises to come from some PDF, some distribution of noise samples. And then signal to noise, we use this for detectability. And this is propagating our losses and our noise power. And then one thing that keep in our mind is that we have target power and we have noise power, and those are what we get in our samples. And we're going to be estimating our noise power from some probabilistic estimate or some way of estimating that noise. And then from our power or signal strength, we'll do things in signal to noise. And with your simulator, you can actually do this now, where you could have your signal to noise, you have a target, calculate its power return as a function of range, calculate its signal to noise, and then this distance here is 10 dB because our cross-sectional area has changed by 10 dB. And so we set thresholds in signal to noise. Noise variance, this is at a given range gate, samples. And then multi-pulse signal to noise. We get into coherent integration. Coherent integration, we have to go back to our unit circle. So we have X and Y. If you were to have a sample that's on this unit circle, you can get its X value and its Y value. If you have successive vectors and they're all the same magnitude, then you can construct, put them head to tail, or tail to head, 1, 2, 3, 4, 1, 2, 3, 4, and then divide by n to get an average. If you just knew that you had a vector that was submagnitude, but you just knew that they had a magnitude of 1, and you added these values, you would add the x component. You'd need to calculate the, you would decompose based on how much is the x component. And then the y would be the sum of the y components. And that's what we did over here. We summed the x components and we summed the y components, but we did it vectorially. If you didn't know, if you couldn't break this down, you'd get an average close to 0. You'd have +1 of the magnitude, -1. So you need to have the phase information. Incoherent integration is when you don't know the phase information.
Professor?
Yeah.
So go back one slide. So we talked about this, I think, at the beginning of class, right? This was what I was talking about. So you're saying that you had to be in a small range so you could do this.
Yes.
Right, so that the phase wouldn't change. I was just saying, if you had a forecast model of the target, you could just maybe rotate, because you'd know that it was supposed to be at a certain point, and you're keeping track of its phase. But
Right.
you're saying that you might not know that until you've done the whole problem and you know the target's velocity and position and stuff like that.
Yes.
Okay.
So if you didn't know this change in position with time, you would take the FFT, and that would fall into one velocity bin. But if you knew, let's see if an example of if you're predicting. predicting where.
I think in GPS you do that. I think in GPS you kind of since you know that the thing is fixed. You know that we know how the phase changes.
Mm-hmm.
You can do a coherent phase lock loop or something, and increase your. Or that's what I was thinking of. But I guess if you have a target, you might not know that the phase is changing unless you know the target's velocity very well and any sort of motion.
Right. I'm thinking of from an antenna, if your Wi-Fi box in your house, it has several antennas in it that are independent. It says, hey, you're over here. It will change the phase of these antennas to make the beam form closer to you. So you're doing FaceTime and everything's fine. Well, my wife's doing FaceTime and everything's fine. Then she moves around the house and she loses connection because the Wi-Fi station has said, you're over here, I'm going to change my phase. It's a little bit different, but it's changing the phase and predicting where she is. Then when she moves, it has to find her again. So if you have some predictive model, you can then predict where the target's going to be. And the idea is that, one idea is that for every target position, there's going to be some measurement uncertainty. What's this measurement uncertainty relative to the fluctuation of the noise? And if we do multiple pulses, since the target hasn't moved very much and the noise is, you're going to get several samples of noise, you can beat down the variance of this noise, and then hopefully this noise variance will be smaller than the variance from your target. And, well, you'll increase your detectability by having fewer noise extensions. And so now you can actually detect a greater distance because you have a higher signal-to-noise ratio. One thing about this formulation, talking about bandwidth and tau, and when you look at other formulations, they've already, some will start out with having tau and power together. So there's a power bandwidth product, and they add in the gain. So how much power is leaving the antenna? Power aperture product is what it's called, aperture product. Aperture would be the size of your antenna or the gain of your antenna. So the phrase is, what's your power aperture product? And that's like, how much energy can you get out? You can either increase your transmitted power, peak power, longer pulse, or increase your antenna. And they would compare systems by saying, what's your power aperture product?
It forms a sync function.
Yes.
But you wrote T over tau, even though it's in frequency domain. I think would that be F over, if it's in frequency domain, what would that be? F over FC? Or?
Gosh. So if you have I
understand what you're talking about, you know.
Time here,
functions.
And is it sync pi over T? But then it gets converted into frequency, and I'm having a hard time. So the transformation, the FFT transformation of a square, FFT transformation of a square wave is a sync function.
In frequency.
In frequency.
You had written
did I put
T over tau. You left it in time.
Time.
I can look it up. It'd have to be F over something. The sync function. The sync function. Sine F over something.
I think that something would be 1 over tau, would it not?
That's what I thought. That's initially what I wrote down, was it'd be F over basically the bandwidth.
F over bandwidth?
That sounds
Yeah, that's the widths of each Fourier transform are inversely proportional.
Yeah.
So something like that anyway.
Something like that's a good way to put it.
There could be a 2 pi somewhere, or
Yeah, there'll be a 2 pi somewhere.
yeah.
And where's the 2? Because is it t on each side? Is it centered or is it offset?
I can do the analysis and find out.
And then these are the calculations that we did before of minimum signal to noise. Given a range, you can then find your unambiguous range or your minimum RCS.
I wasn't clear on something in the previous slide. So you were saying that your minimum SNR, your minimum noise is going to be when you have the bandwidth exactly at the bandwidth of your sink function that you're talking about. I was just wondering, well, what if your center frequency is a little bit off of your bandwidth, your bin, whatever? Does that make any sense, or am I just looking at this? You have FFTs, right?
Yes.
And then your FFT is just going to have a certain bandwidth, like for the transformation, right?
Okay.
And then does it matter if? I think it doesn't. I'm sorry. I'm just trying to think of the math that you have in FFT. You're just going from the time domain signal that you have, and you just do that frequency. It doesn't matter. Yeah, it doesn't matter your center frequency. You don't have bins. I confuse A to Ds with FFTs.
Okay.
That was my problem. There's no, yeah, it doesn't matter because it's a different thing. Yeah. Exactly. Yeah. Yeah.
So big concept idea is that there's the power and of the target, and the noise is received by the receiver. We're going to have this measured power return, and we're going to estimate the noise power, and that's going to be our signal to noise. So we have to remove, if the target power is so great, so like in our simulation, there was 27 dB of between PR and PN, that taking a little bit of noise power away didn't matter. But when PR and PN are close to the same magnitude, they're both near minus 100 dBm. Then that difference is important. So as you get closer to lower and lower signal to noise, then this added noise is important. When you get further away from the noise floor, then this additive, this little bit of noise, doesn't make much of a difference. Does that make sense?
Do you deal with any situations where the signal to noise ratio is negative?
Yes. It's the definition of how we define the noise floor.
I'm thinking more where the return signal power is less than the noise floor.
Yes. Where every single pulse we get back, we're going to be getting noise. If we then process 128 samples, then we're going to say the noise power is the summation of those 28 points. Then there's going to be some little sine wave that's varying. In the FFT process, it will pull that signal out. So let's say this is 0 Doppler. Let's make it symmetric. It's an averaging process where it takes lots of samples, and if you don't have any, there's no frequency dependency of it, right. So it is at all frequencies. It's random. So this is the noise, and this is now frequency, where we've taken samples. It's not the carrier frequency, This is the samples of our A to D. And now I'm going to turn it sideways. Transmit a pulse, take a sample at a range gate. Take a new pulse, take a sample at a range gate. Sample at a range gate. So this is the time sequence at a given range gate. There's noise. That noise is random. Take an FFT of this power, you'll get the power distributed. If you had a constant of 5 at every single time step, take the FFT, it's not varying in time, it is DC. It's non-varying. It will have some magnitude based on the number of points times. And so that will have a DC component. There's no variation. And it would be here. If you had a slowly varying signal, do the FFT, it might follow the next bin. Let's remove that. And then another faster varying signal. And you'd have this curve. Defining signal to noise where it is the area of that is signal compared to the area of the blue. So
All right, so it's integrated power then.
it's the integrated power. But for a single pulse, how would you detect it?
In the noise floor.
Yeah. So for a single pulse, the single power from a single pulse relative to the noise will always be positive. If it's below the noise or within the noise, then you're just calculating noise values. This could be, yeah, could be negative. So I think that was the slides. Questions? Okay. No questions? Is there anyone on Zoom? Do they have questions? Okay. Well, I'll be here. How do we do on time? 6:25. So, Kartek, I think we'll stop the recording here. And if no one else is on Zoom, no questions, we'll call it a night. Okay. Is there some way, do they have questions?
Try this Zoom thing.
Okay, well, I'll be here if they want to ask a question afterwards. But I think we'll stop the recording now, and then if you have personal questions, we can address those. Thanks. Okay.
Are we, should we go to...
Yeah. I'm probably not going to go to those. I'm going to go to the meeting though.
You are?
Yeah.